Hi everyone, I'm Jerry Yurchison, data science strategist, and your main instructor for Opti201. Thanks for joining and listening on the first couple intro sessions to make sure that we're all up to speed and everyone's on the same page. So now we're going to start diving into our main content, and first up is some intermediate modeling concepts that's going to help us propel our optimization modeling to the next level and really have some fun. So let's dive right in. All right, so let's hop into our agenda for this presentation. The first thing that I want to spend a little bit of time on is identifying opportunities for optimization. Not all mathematical optimization sort of applications or problems sort of just jump out at you and say, hey, use optimization to solve me. Sometimes you have to read between the lines. And so we're going to discuss that a little bit to maybe help you identify a couple extra opportunities that you may have missed and may be able to come back to, or in the future be able to identify as like, hey, this would be a great opportunity to use mathematical optimization. We are going to then do a brief Opti 101 recap. So talk about how we approached things during that training, and also sort of recap one of the problems and sort of show some differences between Opti 101 and 201. And then we'll dive into a few intermediate modeling concepts. So modeling logic with binary variables, talk about the famous and or infamous big M, and then start modeling some simple functions using what we've learned. So let's jump right on into identifying some opportunities for optimization. So when you start a project, you may not have a very clear set of instructions or clear goals right off the bat, and you may be sort of searching for what's the right method in order to solve a problem. So what I want to sort of first talk about is what you probably don't hear in these scenarios from from your team leaders, or if you are a team leader, from even if, from your leadership. Sort of this is kind of not how it goes. But although you may be expecting this in order for you to sort of highlight, be able to identify what the right approach is to solve a problem that you're working on. So you may have your manager come in one day and say, all right, team, we have a new project. We're going to minimize the cost of storing and transporting our products while adhering to business rules. And all right, you on the team, or with your team, may say, okay, that sounds pretty rad. That's very straightforward, very clear, and we can get going. And say, "Hey, yeah, that definitely is rad." And maybe able to identify, because going through Opti 101, the building blocks of optimization models, be able to identify those and be like, hey, this is a great application for mathematical optimization. But again, that's not typically how this goes. So let's see what you actually do here. And when you're in these, sort of project meetings or things of that nature, this is typically how it goes, at least partially from my experience, but also from just everyone else's experience that I've ever talked to about these types of things. You sort of get some have a conversation around, okay, here we have this bigger problem. We need to be more efficient in storing and transporting inventory, but we can't significantly disrupt our current processes, and there may be other things that you have to adhere to as well. When you have sort of these more general guidelines in terms of project goals and things that you have to adhere to, that can sound pretty tough. It's you're sort of wading through a big pool of options to sort of say, how can I apply what I know in order to help gain some understanding for this very important problem that your team may be having. So when you have these vague instructions or vague guidelines, you say, okay, well, I guess we can just slap together some process to get some improvement, and maybe we can, apply some smart rules to help sort of maybe reduce some costs or things of that nature. But what I want you to get out of this training and other, Opti 101 and all the other things that Gurobi has put together, once you be able to say, hey, okay, I hear what you're saying, and I can identify these building blocks and say maybe mathematical optimization can be used to minimize our costs, and we can limit the disruptions through our current processes through constraints. And you sort of see how sort of more vague language can be turned into something that is a mathematical optimization problem. So when you are identifying opportunities for optimization and talking with like your leadership about things like this, or other peers and coworkers, or other people that you maybe work on research with, it's you may encounter some hurdles along the way in sort of describing when you describe what mathematical optimization is, and what it, the problems that it solves and its benefits, and all the cool stuff that comes along with it. You may get some pushback, and I sort of want to talk about right now like what some of those feelings may be, and then that may be able to prepare you to sort of work through some of those with your team. So optimization, just in general, when you think about what it is, that there's one solution or one set of solutions that are better than every other thing that you can that's available. That's just sort of a tough thing to comprehend, to be completely honest. It's you know the sort of the finality of it is a little bit yeah, it's a little bit tough to comprehend. So you may get some pushback from decision makers, just sort of when they sort of think about that. And one reason that you may get pushback is because decision makers, they may feel like they're going to lose control if they sort of adopt mathematical optimization or optimization as a whole, as in part of their process. Sort of sometimes the buck stops with them, and sort of leaving it to a black box may not be the best thing for them. Luckily, with the advancements of other techniques like in machine learning, deep learning, so on and so forth, where people are getting more trust in sort of doing things more algorithmically, and using models and all that sort of stuff. So this may be something that you can point to other successes to say, hey, maybe we should try optimization. Some people may feel that, hey, we've already made some improvements, so we're already optimized. I've, did this, that, and the other thing, and we got X% better. So, we're done. Problem solved. But one thing that we've learned through Opti 101 is that there may be more room for improvement, and having a globally optimal solution is one way to make sure about that. Optimization may be viewed as too complex to be useful. That whole concept of all models are wrong, but blah blah blah. That is true. And mathematical optimization models certainly do not capture everything, but again, this could definitely be something that is can be very useful, and the complexity um, is a benefit for mathematical optimization. That's its wheelhouse, particularly when you have a solver like Gurobi in hand. So building the case for optimization can be tough, and luckily we have some resources to help. So check out essentially our website can definitely help for a lot of these things, but we'll be dropping links in as well to sort of to some key bits of resources that we have in order to help you sort of break down any of these barriers. So now let's move on to a quick recap of some Opti 101 material before we head into our intermediate modeling concepts. So for an Opti 101, one of the main things that we were doing is taking understanding the flow from sort of written words or spoken words to a algebraic representation that we're calling a formulation, and then taking that formulation, putting it into code. So step one was we were looking at a decision problem described in words. So a company wants to reduce transportation costs. We need to decide how many widgets to produce at certain facilities, and where should we send them off to for for local supply, and then each of the facilities have a min and max that it can produce, and the distribution locations need to be able to satisfy local demand. So all of these are parts from the remember from Opti 101, sort of the motivating example that I used in one of the early presentations there. Was about producing and sending off widgets. So you hear these problems described in words, and then, well, what we did in Opti 101 was take those words and convert them to an algebraic formulation. And again, at that time, and I still feel this way, obviously, that taking the time to do this algebraic step is super important. Um, and the main reason that it is super important is because when you finally do code a solution and use a solver, the connection between the code and the formulation is quite close, as we saw. There's a lot of similarities between the inequalities, equalities, and expressions that you would build in the code to the formulation. So it's definitely a great way to make sure that you're not missing anything. And again, going from words to the algebraic model, you can make sure that you're not losing anything, and then going from the model to the code, you make sure you're not losing anything to make sure, and this will help you make sure that you're capturing all the realism that you can in the model. So if I had to describe the main goal of Opti 101 in a very short sentence or a couple of sentences, uh, that's essentially how I would describe it. Is the idea of taking a decision problem, translating those words into a formulation, and translating that formulation into the code by identifying the building blocks of optimization models, and being able to go from one to the next. So if that's Opti 101, which for our widget problem that I was describing, and we can see the map here of the blue production facilities and the orange distribution locations. Um, this is how I describe that problem very quickly. Again, we were in Opti 101, we were deciding the number of widgets to make and produce at certain facilities, to send to other distribution locations to meet demand at minimal cost. Very short and sweet. That's Opti 101. And now what's popping up is this is sort of representation of the optimal solution, where we were sending things, widgets all over the place. Even that long, very very long route from Cleveland to South Carolina, that was part of the optimal solution based off of our information. So what does solving a problem at a 201 level sort of look like? Well, it's all of the above, plus considering expanding production capacity at facilities, also maybe potentially opening new facilities or closing existing locations, also while meeting regional requirements where there's a relationship between facilities that are close to one another, all while minimizing cost, but also minimizing maybe environmental impact, and then plus being prepared for various scenarios, including like work stoppages or spikes in transportation costs, or maybe things like significant changes in demand. So there's a lot more to consider at the 201 level than the 101 level. So these are some of the things that we're going to be able to sort of work on modeling and understanding over the rest of this session and throughout the rest of the training. All right, so now that we've sort of remembered, some Opti 101 stuff and feel great about it, let's dive right into a few of the modeling concepts that we're gonna talk about here. So the first intermediate topic that we're going to dive into is modeling with binary decision variables. And this is something we actually hit on a little bit in Opti 101. In both modeling examples, we introduced binary variables, and we saw in the widget example how we can use them to decide if we wanted to expand the production capacity of a particular facility. And in the second example, which had to do with renewable energy and storage, we used binary decision variables to model a battery charging or discharging. So we're going to go back to the widget example a little bit and Suppose we want to link opening a widget production facility to the number of widgets produced there and shipped to other locations. So let's have a nice little diagram of a facility on the left, production facility, and then distribution locations on the right. So we're going to make this pretty visual here. And the production facility, if it's yellow, means it's open. And if it's black, means it's closed. Same thing for the distribution locations. So the question that is important for understanding how to model this is, okay, let's say that my production facility is open. What does that mean necessarily for the distribution locations? And the answer may not be as intuitive as you may think. So this is the first question I want to pose to you, and it's our little quiz time. So in the app or the Hoova platform, you should see a poll on the right-hand side. So if you haven't already answered it, now's the time. This is the question. So the question that I'd like you to answer in that poll, please, is which one of these statements must always be the case? So if a facility is open, we must produce widgets there. If widgets are produced at a facility, then it must be open, or both, or neither. Maybe we don't know much about this at all. So I'm going to give you guys a few seconds to think about it and submit your poll answer if you already haven't. Okay, so actually the answer is B. If widgets are produced in a facility, then it must be open. And we'll discuss a little bit more on the following slides and a little bit later in this presentation on why that's the case. If it's not already intuitive enough for you, which sometimes some of these relationships are pretty complex, and they may not be super easy to understand at first grasp, but yeah, that's what we're here for. So the important thing is that understanding the logic of a system is crucial in optimization modeling, because again, you are trying to mimic and understand a very complex system and model it to be able to understand what the optimal outcomes are. So to understand more about modeling logic with binary variables and sort of how we came to the conclusion that we did at the with the quiz time example, we're going to talk a little bit more about binary variables, but then also a little bit more about how we can use them to model logic. So as we know, binary variables are super powerful when used correctly, when done correctly in optimization modeling. And they represent yes/no switches, on/off, but also true/false. So therefore, let's talk about logic. So we can model a lot of logical statements in mathematical optimization, and in other areas as well, using and, or, not, if, then. So those are a few of the logical operators that are the most common, and we're going to talk a little bit about those. So for us to understand this, let's do a course within a course, I guess. Within Opti201, let's talk about Logic 101. So let's say we have two events, A and B. We say A and B, and we say that meaning that both A occurs, B occurs. A or B, so maybe it's event A that occurs, maybe it's B, maybe it's both, but at least one. We have XOR, so X or B. Maybe it's A, maybe it's B, but not both. Not A, meaning A does not occur. If A, then B means, okay, when A occurs, the if part, then B is guaranteed to also occur. And we have A if and only if B, which means if A, then B, and if B, then A. So it's taking an if-then statement and putting one around each and as well. So in addition to that, there's a few sort of logical equivalencies. So meaning these two groups of sort of logical statements, these two logical statements are exactly the same in terms of their meaning and what they, whether or not their overall truthfulness and falsefulness. But these are a few ways to help sort of translate logical statements that help with mathematical optimization. So one is called De Morgan's laws. And essentially what that is it takes a not and distributes it amongst an A and B statement and also an A or B statement, but I sort of put out the A and B there so you could see. So not A and B is equivalent to not A or not B. And this is similar for or as well, where it replaced the and the or and you got the same thing. So this is a way to negate an and statement or to negate an or statement. If then contrapositive, so you may have heard that statement before, but this is again another super powerful equivalency to help you sort of model some of these logical statements, and that says if A then B is equivalent to if not B then not A. So you switch the A and B and you put not in front of each of those. And those two statements mean the exact same thing. And then if you want to translate if then to an or statement, so if you have if A then B, that is equivalent to not A or B. And if we had more time for Logic 101, we can get into why all of these are true and build Venn diagrams and all this sort of stuff. So if this is unfamiliar to you, then you might have to take some of this as just the truth now, but there's a lot of resources about these logical statements and equivalencies. So if that's something that you want to dive into more, I think that'd be pretty awesome. So now that we've completed an entire course of Logic 101, let's go back to the widget problem again and sort of explain why quiz time went the way that it did. So again, we're considering the widget problem from Opti201, modeling example 1. And a reminder on the decision variables, specifically for that example. We had sets P and D that we sort of referenced a little bit ago for production facilities and distribution facilities. And we had, so XPD was the number of widgets produced in production facility P and shipped to distribution facility D. So now to model this, since we're talking about modeling logic with binary variables, let's create a new binary decision variable for deciding to open a production facility. So YP is 1 if we decide to open production facility P, and 0 otherwise. So 0 if it's going to close. So as we learned in Opti101, constraints relate two sides using less than or equal to, greater than or equal to, or strictly equal. So how we model this constraint that we've been talking about is through what we call big M constraints. And the proper constraint, or the way to write this in terms of inequality and our decision variables, is XPD is less than or equal to some number M times YP. And now we're gonna talk about why this is the case and why this constraint works from a logical perspective. So let's say that everything is off. We don't do anything. We have no production, we have no distribution, anything. Then this inequality is satisfied. We have a green check. Everything's good. 0 is less than or equal to 0. That's certainly true. So let's say that we then turn on XPD, more or less. We start producing from a particular production facility and shipping to a distribution facility. So we essentially, again, make the left-hand side of this positive. So a positive number cannot be less, or a positive number cannot be less than or equal to 0. So our inequality is no longer true. So that means we then force the facility YP to be 1 in order to make this true. So a positive value on the left-hand side will be less than or equal to what's on the right-hand side, provided our M is big enough, hence big M. So essentially what we have is if XPD is positive, then YP is going to be 1. Now let's think about what happens when we close down facility P. So if we were to turn it off, then we have a right-hand side of 0 once we turn that off. So therefore, 0 can't be greater than or equal to a positive number. So then that forces the left-hand side to be 0. So the way to interpret that is if we close facility P, or if it is not open, then XPD must be 0, meaning we cannot produce widgets at that facility. So essentially, if YP is 0, then XPD is 0. And these two statements that we sort of talked about, if XPD is positive, then YP is 1. And then if YP is 0, then XPD is 0. Those are contrapositive if-then statements, so logically equivalent. So either way that you think about it would make sense. And that's why modeling this statement with this inequality works, because either of those ways of thinking about it match up with the inequality. So that is it's essentially what big M constraints are in a very, very quick nutshell. And we're going to work with more with them as we go. All right, so we're going to head back to the widget problem again, as we've been hitting on over the last little while. So let's take a look at the optimal solution for essentially the base case that we looked at during the modeling example 1 from Opti201. So if you were someone who was in charge of this process and in charge of production and shipping of widgets from production facilities to distribution locations, and someone brought this optimal solution to you, you may look at a couple of the shipment values and be like, I don't know if that's really doable. I don't know if we can actually implement this. And something like this is very natural in the process of creating an optimization model. You might get some solutions and be like, I'm not sure if this is actually really feasible. So that allows for some iteration and some improvement to make your model more real. So if that's something that you see happen, you get weird solutions and you're wondering, oh geez, what do I do next? Then essentially keep in mind that just with any other type of model building, in machine learning or in optimization or anything, it is an iterative process. So definitely take some time to work through that. But the particular value that I'm talking about is the decision to ship only 2 units from Cleveland to Nashville. And why that may be an issue is because that's such a small number that it may not be possible for sort of like, if you're thinking about mass production of widgets, this sort of small shipment may not be feasible, may not be doable for you. Or you may just you may be able to do it, but maybe the cost that we're quoted here may not be valid for such a small number. So there's a bunch of reasons why you think that this too may be a bit of an issue. So you may be thinking, okay, how am I supposed to fix this? Well, all right, let's add a constraint saying that the shipments must be at least C units. Okay, we need to have it at least be like 20 or 40 or something like that, or 50. But if you add the constraint that I have here saying XPD must be greater than or equal to C, that is going to require every production facility to ship to every distribution location at least C units, if written like this. And that's definitely not what we want. We want to be able to choose some of these some of these arcs or connections between production and distribution to be 0. That's definitely something that we want. So actually the way that we want to think about this is, let's scribble out that's wrong. We don't want that constraint. We want to say if widgets are shipped from P to D, then it must be at least C units. And these are saying 2 very different things, because one is saying everything must be at least C. What we have on the bottom is saying that if we decide that any should be sent from one location to another, then we implement this lower bound. So we're going to definitely look a little bit more into how to model this in the hands-on modeling session. Check mark. So that's enough widgets for now. And like I mentioned, we're going to dive into a lot more with that problem and how we can expand it to make it more real. So what we're going to talk about now is modeling some very simple functions that are useful in mathematical optimization, but then also sort of understanding how they relate to the logic stuff that we've been talking about over the last few minutes. So let's consider a set of decision variables x1 through xn, and we want to relate a decision variable y to the max across all of those x decision variables. So let's say that we want y to be greater than or equal to the max of xi for all over I. That means that y has to be greater than or equal to each xi, so all of them. So another way to think about that, again, sort of think about the logical stuff that we've been discussing. If y is greater than or equal to all of them, that means it's y is greater than or equal to x1, and it's greater than or equal to x2 and x3, so on and so forth. So a nice little visual for that is, say we have a bunch of points, that means y needs to be in that shaded region on the right. It needs to be greater than or equal to all of them. So it's greater than the first one and the second one and the third one, and so on and so forth. So we can say that y is greater than or equal to the max if it's greater than or equal to all of them. Say we want to relate y to be less than or equal to the max. That means that y is less than or equal to at least one xi. It could be less than or equal to more of them, that's fine. But if it's less than or equal to max, less than or equal to the max, then it must be less than or equal to at least 1. So that means y is less than or equal to x1, or y is less than or equal to x2, or x3, so on and so forth. So that means we would have y being in this shaded region on the left, much larger, but means it must be less than or equal to one of our x values. So if we want y to be equal to the max, that means both hold. So if you think about two numbers or two values, and you say y is less than or equal to x and x is less than or equal to y, then the only thing that you can say is that y is equal to x. So if both of the conditions above hold, that means y is equal to the max. So we can see how and statements and or statements can come into play with modeling the max between decision variables. So you may be asking, okay, what about the minimum? How does that work? That's an exercise for fun. So I encourage you to sort of think about what relating a decision variable y to the minimum across the set and how that would play out for y being greater than the min, less than the min, and equal to the min. I'll give you a hint about the equal part. It's exactly the same as below, but the other ones are slightly different. So a good exercise to go through. So the next simple function that we're going to look at is absolute value, and we're going to see how that can be decomposed into logical statements, which will then help us model such things in mathematical optimization models. So let's consider the absolute value of a decision variable, and all of these statements are true of just numbers in general. It doesn't need to necessarily be optimization decision variables, but since this is the context that we're talking about it, let's just call it a decision variable. So let's say that we want the absolute value of x to be less than or equal to c. So what does that mean? If the absolute value of x is less than or equal to c, and let's make a we have to make a quick assumption about c. C has to be non-negative. for this to be true because an absolute value is non-negative. But what that means is that x is less than or equal to c, and x is greater than or equal to negative c. So you might be thinking, what does that look like on a number line? Oh, okay. Here we go. So the absolute value of x less than or c, all of these values in the shaded region in the middle satisfy that. So how do we talk about x, the absolute value of x being greater than or equal to c? Well, that means the absolute value of x greater than or equal to c. That means x is greater than or equal to c, or x is less than or equal to negative c. So we sort of need to be on more extreme ends. So you can see that, yep, let's just shade in the opposite side, and these values in the shaded region would then satisfy the original inequality. The top one, where x is less than or equal to c and greater than or equal to negative c, that's pretty easy to model from an optimization perspective. It's just two inequalities. The one on the bottom, though, that gets a little bit trickier because, again, one of the sort of general assumptions of mathematical optimization is that the feasible region, the set of all possible solutions, is what we call convex. And what we mean by convex is if you take 2 points in that region, you can essentially draw a line between those 2 points, and that line then remains in the feasible region, remains in the set. But as we can clearly see, that's not the case in this sort of lower example here. So these are disjoint. So we need a little bit of work to make that happen. And that's where binary decision variables can come in and play. So we'll sort of see more about how to deal with these types of situations later on. So now that we established a little bit of like, hey, maybe modeling with max and min is kind of a cool thing and maybe useful in mathematical optimization and optimization in general. So let's take a look at a scatter plot here. We have a bunch of points, and our goal is to find a new point that is essentially a short distance from the set of blue points. So that's a kind of a vague description of what we want. Maybe so that comes from the beginning of our talk, where we're talking about how maybe not all optimization problems are super clear cut, but so we just want something that is a short distance from the set of points. So your typical data science, operations research, math, anybody like that is like, okay, well, I'm going to minimize the sum of the square distances and find a point that does that across all points on our scatter plot, and that's going to be what I use as the point that is a short distance from everything. Well, what we can see in that bottom left corner of the scatter plot is that there's a bit of an outlier. So the question is, how important is that outlier? If we're talking about something like something about fairness and maybe this is the distance that people need to walk to get to something, maybe some stores or like a polling location for voting or anything along those lines, maybe we need to make sure that outlier is actually treated a little bit more fairly than some of the square distances would treat that. So so what we can do is we can do what we call a min-max objective. Have it here called other names, but essentially what we want to do is we want to minimize the max squared distance. So instead of minimizing the sum of square distances, we minimize the max squared distance. So when we do that, we have 2 new points that pop up. We have an orange one and a purple one. And the typical objective is the orange point. So that is the point that you get when you minimize the sum of the square distance, and the purple point is what you get when you minimize the max square distance. And from a perspective of what's sort of most fair for all of points, if you want to think of it from that perspective, then you may want to go with that purple point instead of the orange one. So that's one instance where actually using something like this would be a better choice possibly. So specifically the first objective minimizes what we call the L2 norm, which is what we talk about with distance. And the min-max, what that does is that minimizes the L infinity norm, which the L infinity norm is just essentially just defined as the max of a set of numbers. So again, we're minimizing the max, the max squared distance. So I hope this was a pretty interesting example. I thought so. So you may be thinking, is there a more general way to formulate uh, a, working with a set of constraints and logically maybe choosing between one of them, or sort of generalizing what we've been talking about so far? And the answer is yes. So let's say we have a set of j constraints and we want to consider some subset k less than or equal to j. So we have f1 through fj and r1 right hand sides of those constraints, r1 through rj, and we want to implement some constraints to make sure that some of these happen or some of them don't, things like that. So maybe asking, okay, how do I go about doing that? Well, the answer is big M. And specifically, let's add zj binary variables multiplied by some corresponding m to each of the right-hand sides. So now we have this, all of these inequalities, and these will sort of have the same sort of function that we talked about earlier on, of essentially turning on and off each of the ability to enforce these constraints. So if you think about it, if each of the z's, if a particular z is 1, that means that the right hand side is going to be some really, really, really large number, meaning that we're allowing that constraint to be violated with respect to just the right hand side r, lowercase r number. We're allowing the function of the decision variables to go past r if one of the z's is equal to 1. If it's equal to 0, then 0 times the m is 0, so we're just left with the original constraint. So what this is allowing us is allowing us to control the number of these alternative constraints that we're allowing to be violated. So if we want to say, okay, we have this set of constraints, and we want at most of them, we want to allow at most k of them to be violated, then we then add an additional constraint that says the sum of these z's that we added must be less than or equal to k. So we're putting an upper bound on the number of constraints we're allowing to be violated, or the number of constraints we're allowing to go past the original right-hand sides. If we want at least k, then you just switch around the inequality sign and say the sum is less than or equal to k. And I think you can know where we're going here. If we want exactly k constraints to be violated, then we say the sum is equal to k. So this provides a sort of a general framework, because a lot of these statements that we were talking about can be reduced to something like this. But another thing that I think would be a good thing to think about is how would this change? How would the formulation change? How would the use of the auxiliary variables change if we were determining the number of constraints that need to be satisfied? So this was allowing certain number of constraints to be violated. If we wanted to sort of switch that up a little bit, how would that look? What would we need to change? Good exercise for you. So that is it for this first session. I really hope you got a lot out of it. So the next thing on the agenda is hands-on modeling and coding, talking about all of the good stuff that we went through now. So I will see you then.